I continue working out problems from the problem sets where there's going to be exam problems that are just like these problems that I'm working out. So this is problem number 2 from problem set 2. And there's going to be a problem on the upcoming exam that is just like this. And so we're given a function Vx. So this is the x component of velocity. And it's Vx is a function of time. So I'll say Vx of t. Because when we plug in different t's for this function, we will get different x components of velocity corresponding to those different t's. And so in this specific case, it's 2t squared meters per second. If I plugged in, say, t equals 0, it'd be 0 meters per second. If I plugged in t equals 1, it'd be 1 squared, which is 1 times 2, it'd be 2 meters per second. If I plugged in t equals 2, it would be 2 squared, which is 4 times 2, to be 8 meters per second. We are told that t is in seconds. Those brackets around t is for dimensions. We're also told that the initial position of this particle, which we'll call x naught, is 2.0 meters at t naught, which is t equal to 0 seconds. So we are asked for part A, at t equal 1.0 seconds, what is the particle's position? Which is another way of saying, what is the x position as a function of time, where we will plug in 1 second to get our answer. How do we do this? Because we're only given our velocity as a function of time. This is where calculus can be really helpful. It turns out that if you have position, the derivative of position is going to be velocity. The derivative of velocity is going to be acceleration. You can think of position in the x direction as some function x of t. You can think of x double prime as the velocity as a function of t. You can think of x triple prime as the acceleration as a function of t. But just as we can take derivatives, we can also take integrals. So I can go from, say, a function of position versus time and take the derivative and find the velocity as a function of time. Or I could take the integral of the velocity as a function of time, and that gives me the position as a function of time. And that's precisely what we're going to do here. We're going to say x is a function of time is going to be equal to some indefinite integral of this function Vx of t dt. When I take this integral, I'm going to plug in the specific function, which is 2t squared dt. And when I take that integral out, I'm going to get 2/3 t cubed plus some constant c. If I was to take the derivative of 2/3 t to the cube plus c, the exponent 3 would come down, so you'd have 2/3 times 3. The 3's would cancel, you'd have a 2, which is what you want. And then the derivative of a constant is 0. And so if I took the derivative of 2/3 t cubed plus c, I would get 2t squared dt. And that's the idea of doing an indefinite integral. But because it's an indefinite integral, we're also going to have to figure out what this constant is. And so fortunately, we are told that when we have t equals z seconds, the position of this particle is at 2 meters, which is to say x of 0 is equal to 2/3. So I'm going to take what I just integrated and plug in t equals 0. So that's going to be 2/3 0 cubed plus c, Well, you can imagine 0 cubed is 0, and so that's just going to equal c, but we were told that x naught equals 2 at t equals 0 seconds, and so that's going to be equal to 2.0 meters. So now we know what our constant is, and so we can say more specifically, I'll change the color here, we can say that our x of t is equal to 2/3 t cubed plus 2. That is our x as a function of time. And so now if we're asked, okay, well, what is the position when x as a function of time is t equals 1 second? So if I put 1.0 seconds in here, I get 2/3 1.0 seconds cubed plus 2. 1 cubed is just 1, and so it's going to be equal to 2/3 plus 2, which is equal to 2/3 plus 6/3. I'm just rewriting 2, which is equal to 8/3, which is approximately equal to 2.67. Okay, so we started with our velocity as a function of time. We took the indefinite integral. We knew the initial condition, and so that allowed us to solve for the constant. That gave us an overall expression of x as a function of time. And then we were asked in part A just to figure out, okay, well, where is it? What is the x coordinate at t equals 1? And so we plugged 1 in. So that's part A. And so moving on to part B. In part B, we are asked at t equals 1.0 seconds, what is the particle's velocity? And again, this is all in the x direction. Okay, so this is to say, if we have some function vx of t, then this t equals 1 second is what we would plug in right here. So let's go back. We have already this expression vx of t. It's equal to 2t squared. So going back, vx of t equals 2t squared, and we want to solve this for when t equals 1.0 seconds. So we go vx of 1 equals 2 times 1 squared. 1 squared is 1, and so that's just going to be 2.0, and it's in meters per second with velocity. Part C of the problem, it asks at t equals 1.0 seconds, what is the acceleration in the x direction? All right, remember I talked about how position is a function of time. You can take the derivative of that and get velocity as a function of time. Take the derivative of that, you get acceleration as a function of time. And then you can integrate back. You can start with acceleration as a function of time, take the integral of that, get the velocity as a function of time. You can take the integral of the velocity as a function of time and get the position as a function of time. Well, right now, looking back, we've got velocity as a function of time given to us, and we use integration to figure out position as a function of time. Part C is going to ask for acceleration, and so remember we have the velocity, and so if I just take the derivative of the velocity, so more specifically, if vx as a function of time equals 2t squared, then I can write d so this is just taking the velocity as a function of time and then taking the derivative of that as a function of time. And so that will equal, if velocity as a function of time is 2t squared, if you take the derivative of that, and really quickly, let me also say this is another way of saying v prime x of t. And so if v x of t equals 2t squared, if I'm going to take the derivative of that, the exponent 2 is going to come down and multiply by the coefficient 2. And so you're going to get a 4t. And we want to evaluate that at t equals 1. And so quite simply, since we know that v prime is going to be the acceleration, we can say that the acceleration in the x direction as a function of t is equal to 4t. And so if we're asked what is the acceleration when t equals 1, it's quite simply 4 times 1 equals 4. And so the answer to part C is that the acceleration as a function of time at t equals 1 is going to be equal to 4 meters per second squared. Just to review, we were given velocity as a function of time. In general, position is a function of time. If we're talking about the horizontal x direction, we'd say x of t. We could say the derivative of that is the velocity as a function of time. So we could say there's x prime, which is the first derivative of x, which is the velocity, and x double prime, which is the second derivative of x. And then we can also work backwards. We can start with, say, the second prime of x, which is acceleration. We can integrate that. That gets us back to x prime, which is the velocity. We can integrate that, and that gets us back to x, which is the position. So we did a little bit of both in this problem. We had velocity as a function of time. We had to integrate it to find position as a function of time and then figure out what the position was at a given time. But then we also had to figure out, if we are given this velocity as a function of time and we're given a time, what's the velocity at that time? And then we were also asked a question about acceleration, and we knew that, well, we could take the derivative of the velocity and plug in the appropriate time and get the acceleration for that time. So that's a recap of problem number 2. So this is problem number 8 from problem set 2. There will absolutely be a problem on the next exam that is just like this problem. And so this problem, we have a supply plane. The supply plane is flying horizontally, and it's a certain height above where it needs to drop supply packages. So more specifically, we are told that based on the current altitude of the plane, when it makes a drop, the change in y of the package being dropped is going to be equal to negative 160 meters. That's going on the conventional positive x is to the right, positive y is up, meaning negative x is to the left and negative y is down. We're also told that the velocity in the horizontal direction of the supply plane is 150 meters per second. So we need to think about what's happening both in the horizontal direction and the vertical direction. First and foremost, in the horizontal direction, when the package is dropped from the supply plane, there are only forces acting downwards. So imagine right at the moment that the package leaves the plane, you would only have the single force of gravity acting down. We are not incorporating air drag into this problem. If we did incorporate air drag into this problem, then there would be some force that opposes the direction of motion. but we're not going to worry about that right now. And in fact, we're still doing kinematics, and so we really haven't unpacked the idea of force yet. So the basic idea is that only in the vertical direction is there acceleration, and more specifically, the acceleration is the gravitational acceleration towards the center of the Earth, which is 9.8 meters per second squared. So even though we see this object come out of the plane that's moving horizontally, and we think that the object, right, it has a combination of both horizontal and vertical. We're getting into 2 dimensions now. The thing is that it's easy to conflate the horizontal motion with the vertical motion. We see it together, but in reality, it's only in the vertical direction that there's any acceleration. There's no acceleration in the horizontal direction when the package gets dropped. It has the same velocity as the plane when it gets dropped. And it stays at that velocity because there's no acceleration in the horizontal direction. If there's no acceleration in the horizontal direction, that means the velocity doesn't change. So whatever the velocity is horizontally of that plane, which is 150 meters per second, it's going to stay that way. So if the velocity is going to stay what it is because it's not accelerating in the horizontal direction, then we know that whatever the horizontal displacement is of the supply package, it's equal to whatever that original horizontal velocity x is, which is 150 meters per second, multiplied by t, which is the time that elapses from when the package is dropped from the plane to when it hits the ground. So we're going to go ahead and keep this delta x, this displacement, in our back pocket, because once we know how much displacement the package is going to move in the horizontal direction, then we just have to know that we have to drop it that distance before we get to the exact place that we want to drop it. So knowing what t is requires us to now just think about the motion in the vertical direction. And so more specifically, we can think of delta y as equal to whatever the initial velocity in the y direction is, multiplied by t plus 1/2 a y, that's the acceleration in the y direction, t squared. Okay, this is one of the kinematic equations for constant acceleration, which when we're talking about gravity, g is a constant acceleration. And so this equation gets a lot simpler when we take into account the fact that when you drop something, when you originally drop it, its vertical velocity, the velocity in the y direction, is 0. And so that term goes away. The acceleration in the y direction is just the acceleration due to gravity. And so the delta y from when you drop the supply to when it hits the ground, that is going to be negative g over 2 t squared. I plugged in the 9.8. The 9.8 has a negative sign because it's going down, and we've defined up as positive. So we now know that we can express the vertical displacement as a function of t. And even better, we already know that this equals 160 meters dropped, which is negative 160 meters if you think about negative being down. And so this is negative 160 meters. That's nice because the negative signs cancel out. So what I'm going to do is I'm going to multiply both sides by 2, and I'm going to divide both sides by g. That's going to isolate the t squared. So I'll have a t squared equals 2 times 160. Again, the negative sign canceled out. And then I'll have my 9.8 meters per second squared. So now I want to solve for t, and that means I just need to take the square root of both sides. And so the square root of t squared is t, and that equals the square root of 2 times 160 divided by 9.8. And so when you plug these numbers in, two times 160 is 320. So we'll just keep this as 320 divided by 9.8. And I'm going to show you how we'll plug this back into solve. Because again, so this is the time it takes to fall 160 meters in the vertical direction. Okay, so that's how much time moving in the horizontal direction at velocity Vx we have to take into account for when we want to drop the package. Because obviously if we drop the package when we're right on top of where we want to drop it, the package still has horizontal velocity, so it's going to keep flying horizontally because it's going both horizontally and vertically, and so it's going to obviously miss where we want to drop it off. So we have to figure out if a certain amount of time elapses for the package to drop exactly 160 meters, how many horizontal meters would be covered in that distance, and whatever that is, then we need to figure out where we want to drop the package, and we need to subtract from before we get to that place, and that's where we drop it. So by the time it has the time to drop the vertical distance, it will have covered the horizontal distance from where we dropped it to where we want it to drop. We have t now, and remember in our back pocket we had the expression for how much horizontal distance is covered. And so this equals 150 meters per second. That was what this velocity in the x direction was. And then we've solved for t now. The t that we solve for is the t it takes to drop the 160 meters. And so that is the square root of 320 divided by 9.8. Plug this into a calculator, which I'm going to do right now. 320 divided by 9.8, square root of that, and then multiplied by 150. I get, and I'll put an approximate sign here, 857.14. On the exams, I'm going to ask you to take your numerical answers out to 2 decimal places. That's what I mean by 2 decimal places right there. So to review, there's both horizontal and vertical motion taking place. We can break the problem into a horizontal part and a vertical part. We know that when we drop the package, a certain amount of time is going to elapse before it hits the ground of where we want to drop it. We know we're 160 meters above the ground. We know that the acceleration is due to gravity. We know the acceleration is constant, so we can use our constant acceleration equations for kinematics, and more specifically we think about kinematics in the y direction, and we can use the expression that the change in y is equal to the initial velocity in y multiplied by t plus 1/2 times the acceleration in y multiplied by t squared. And so that allows us to figure out the time it takes to drop the 160 meters. When we know the time it takes to drop the 160 meters, we can then go to the horizontal component of the problem. We know that there's no acceleration, so the velocity remains constant. So we simply take the velocity in the x direction and multiply it by the time, and that'll tell us how much displacement in the x direction there is. And so that's how much before we get to the location we need to drop the package in order for the package to land where we hoped it would land. So that concludes problem number 8 from problem set number 2. This is problem 10 from problem set 2. This problem is a problem in which vectors are going to come in really handy. And there's also an important lesson to learn with respect to an XY coordinate system and how theta, the angle theta on an XY coordinate system, is related to trigonometric functions like sine and cosine and tangent. So this is a problem where there's a kayaker that wants to paddle north across a 100-meter wide harbor. So before we go any further, let's make sure we get our coordinate system mapped so that we have the cardinal directions corresponding to x and y. So we typically, with cardinal directions, we have north going up, we have east to the right, we have south down, and we have west to the left, we typically have positive y up and positive x to the right, negative y down, and negative x to the left. So when they say it goes north, this means goes in the positive y direction. And more specifically, we know that delta y is going to be equal to 100 meters. That's the width of the harbor that the kayaker wants to paddle north across. And the key here is they want to continue in a northbound direction, i.e. in a positive y direction. And so to do that, it turns out they're not able to just point the kayak directly north. They can't do that because there happens to be a current. The water is flowing to the east, which to the east we mean in the positive x direction, at 2 meters per second. So V current equals plus 2.0 meters per second because it's going in the positive x direction, which is east. So if you can imagine, if the kayaker just aimed the kayak north and just paddled north, sure, they would be going north, but there'd also be an x component due to the current that would make them start to drift to the right, and so they wouldn't go straight across the harbor. So to solve this problem, the kayaker has to figure out how to aim the kayak so that even with the current flowing to the east, the kayak is still going to go straight across the harbor. And so the key to that is to have the kayak aim itself. And let's go ahead and put a coordinate system on here. So if this is due north, which is the same as our plus y, we want the kayak to be aimed such that if there is some current that's flowing to the right, the kayak, if it's aimed properly, will have an x component that is equal and opposite the velocity of the current, what we will call v kayak x. And this vector right here, the overall direction, is v kayak. Now, I want to also use this as an opportunity to show you how you can use SOHCAHTOA to figure out with trigonometry how you can use the different legs of a triangle to figure out the sine, the cosine, and the tangent. So what I'm going to do is I'm going to define this angle right here as phi. That's in contrast with the angle that I just drew, which is the angle swept from the positive x-axis to the vector. That is theta. Now, if you look at the two of them, if you were to sweep from the positive x-axis to the negative x-axis, that would be 180 degrees. So phi plus theta equals 180 degrees. I'll write that out. And so therefore, if I want to isolate phi, I'm going to subtract theta from both sides, meaning that phi is equal to 180 degrees minus theta. This is going to be important later on because there's an important lesson about knowing how theta is defined when using these trig functions. So I want to reiterate that if there's this current that's going to the right, if we're going to go straight across the harbor, then the x component of our current has to be equal and opposite. So we need to figure out what that angle phi, green, you see the green phi? We need to figure out what that angle is. And when we do that, we can break the kayaker's velocity into x and y components. And then we already know that the x component has to be equal and opposite the current. Just to be complete here, there's also a y component, v kayaker y. And now what I want to do is I want to blow up that triangle such that this is v kayaker, this is v kayaker x, this is v kayaker y. And now I want to invoke SOHCAHTOA. This acronym helps you remember that the sine of an angle, and in this case we define this as phi, so sine of phi equals opposite over hypotenuse. And then we have to define what our opposite side is, and so the easiest side to identify is the hypotenuse. That's going to be the leg of the right triangle that spans the two perpendicular sides, because these two legs are perpendicular. And so it's also the longest leg of this right triangle. And so the hypotenuse is the v kayaker. And so now we have to figure out which side is opposite, which side is adjacent. So if you have an angle of interest, you want to go directly opposite that angle, which happens to be right here. So the y component is opposite, and that leaves the adjacent component right here. So now that I've defined what those are, you see how I have sine phi equals opposite over hypotenuse? Well, that's equal to vk y divided by vk. And so I can multiply both sides by vk, and I get vk sine phi equals the y component. Now similarly, using SOHCAHTOA, so that was using so, let's use ka now. And so I'll do a different color here. Ka means that the cosine of phi is equal to the adjacency, the a and the h over hypotenuse, and that is equal to vkx divided by vk. And so similarly, if I multiply both sides by vk, I get a vk cosine phi is equal to the x component of k. Now, if I wanted to, I could go even further. I could use TOA. All right, so I use so, ka. Now let's do TOA. We're not going to need this for the problem, but I'll just be thorough here. The tangent of phi is equal to the O. This is a TOA, so T is tangent, O is opposite, and A is adjacent. And so the opposite side is going to be vky, and the adjacent side is vkx. So that's how you're going to get your different trigonometric functions from this right triangle. So now remember, we want to go straight north across the harbor. We don't want any derivation from directly north, which is the same thing as directly in the y direction. And so that means that we need, for the x component, that's what this term is right here. That's the x component of the kayaker's velocity. It's the same thing as what I point to right here. That needs to be equal and opposite what the velocity of the current is. We know what the velocity of the current is, though, so we know that the velocity of the kayaker's direction, the x direction, is just equal and opposite that value. The velocity of the current, as you can see right here, is plus 2 meters per second squared. And so that means that the velocity of the kayaker in the x direction is equal negative 2.0 meters per second. That's going to be helpful because it's going to allow us to determine the angle at which the kayaker needs to travel straight across the harbor. This is the first part of problem 10. It asks you which direction should the kayaker paddle to travel straight across the harbor. We know that the cosine of phi is the velocity of the kayaker in the x direction divided by the velocity of the kayaker. We are also told that the velocity of the kayaker is equal to 3.0 meters per second. This allows us to take this equation right here, and we're going to be able to solve for phi because we already know what the velocity of the kayaker in the x direction is. It has to be equal and opposite the velocity of the current. So that's what this is right here. So this is going to be negative 2.0 meters per second. And we know what the velocity of the kayaker is. That's 3.0 meters per second. And so the meters per second cancel. This is equal to negative 2/3. And so if we want to figure out what the angle phi is, we take the arc cosine. So cosine minus 1 of cosine phi equals the angle. So similarly, if we take the arc cosine, or sometimes the inverse cosine as it's called, then if we take that to both sides, we are going to get phi is equal to the inverse cosine of negative 2/3. And so I'm plugging that into my calculator right now. When you take the inverse cosine of 2/3, and this is an important thing to point out here, you get 131.81. On your exams, I'm going to ask you to take your answers out to 2 different decimal places. And so just to be safe, take things out to 2 decimal places. Now here's the thing. We got to be careful. The calculator just told us 131.81 degrees. But go back and look at phi, how I defined it. That doesn't look like 131.81 degrees. That looks like something less than 90. Now, what's going on here is that when we're talking about angle theta and how it relates to these trigonometric functions, it's defined by an xy coordinate system where theta equals 0 when we're talking about a vector that's pointing precisely around the positive x direction. I'm going to do another screen here just to try to explicate this a little bit better. So imagine we have, say, here's scenario 1, and we have some vector that points precisely in the positive x direction. Well, in that particular case, theta would equal 0. If we had some later time where the vector was pointed like this, now we have some theta that is non-zero. But the point here is that theta increases as we move in a counterclockwise fashion. So for example, like right here, theta would be 90 degrees. And you could probably imagine we could keep sweeping. So if I had my vector over here, theta would now be like this. Now another way in which you can think about this is that you have quadrants. You have the first quadrant, the second quadrant, the third quadrant, and the fourth quadrant. This should be IV. In the first quadrant, you're going to have a vector that's either, directly around the x or something like this or something like this. In all of those cases, you can imagine that has a positive x component and a positive y component. In quadrant number 2, you can imagine different vectors. it's going to have a positive y component, but it's going to have a negative x component. Vectors here in the third quadrant are going to be having both a negative x component and a negative y component. And in this quadrant right here, they're going to have a negative y component and a positive x component. Now go back to our problem here. We have essentially, and I'll highlight again, this vector of the kayaker's direction, that is in quadrant, if you look here, that's in quadrant number 2. And so in quadrant number 2, you can see that the y component goes up, so that's positive, but the x component goes to the left. That's negative. And that's reflected right here. Do you see how we have the -2? We knew that if the current was going in the +2 direction along the x-axis, then it's going to be -2 to balance it out in the negative x direction. So when I plug those numbers in, remember, theta starts at the x-axis, okay? And it sweeps going counterclockwise, and it gets bigger and bigger. So because I threw into my calculator a -2, which is a negative x component, and a +3, which is a positive y component, my calculator kicks out 131.81. That's precisely because my calculator is defining theta like this, where it starts at the x-axis and sweeps. And so what my calculator told me is actually theta, not phi. Now this is actually nice because the first part of the problem asks for an answer where you are going to talk about if the angle was defined at the positive x direction, what would the angle be? And so the problem can be answered as the angle is 131.81 degrees north of east, which is to say that you start due east and then you sweep 131 degrees. However, because I want to use SOHCAHTOA and just use that right triangle to figure out my x and y components, I know that phi can also be defined if you start going directly west, i.e. directly the negative x direction, and you sweep clockwise. And so I just have to be careful here. If I get a number that doesn't make sense with how I set up the problem, I have to look at the problem and think, okay, well, how did I define things? How did I define my angles? And that 131.81 clearly is not phi. It's theta. But you can define phi as I showed you 180 minus theta. And so that means it's equal to 180 minus 131.81, and so that is equal to approximately 48.19 degrees. That makes more sense, right? This phi clearly is something that is less than 131.81 degrees. That happens to be 48.19 degrees, which makes sense. If you add 131.81 and 48.19, you get 180 degrees, which is, if you span from negative x to positive x, that's exactly 180 degrees. So we're in really good shape now. You could, for your answer on Pearson, you could say it's 131 degrees north of east, or you could say it's 48.19 degrees north of west. Either is saying the same thing, but in terms of figuring out our components, it's going to be easier to be able to just look at the right triangle where you have the kayaker's velocity in the second quadrant, its x component being negative and its y component being positive. So more specifically, we also have our relationship where we can relate the angle, which we now know, the kayaker's velocity, which we now know, and we can figure out what's the velocity in the y direction when the kayaker orients the kayak at an angle of 48.19 degrees north of west, or 131.81 degrees north of east. So I'm going to go back to blue, and if VK sine phi equals the y component of the kayaker, that means sine of phi is equal to the VKY divided by VK. And so actually I thought of an easier way of solving this. Instead, we already know what that angle phi is. It's 48.19 degrees. So I can directly say that VKY is equal to VK sine phi, and that's equal to 3.0 meters per second sine, and so here's that angle that we just solved. It's 48.19 degrees. And that tells us how, if the kayaker is orienting the kayak at 48.19 degrees north of west, it tells us what the velocity in the due north direction, i.e. in the positive y direction, is. So you can solve for that, and so then we can now do a simple kinematics relationship where if we are moving at a constant velocity, then the distance that we cover moving at a constant velocity is quite simply the velocity multiplied by the amount of time that's elapsed. If you think of velocity as meters per second, you multiply that by seconds, you get meters. So I'll write this out as delta y, and this is in the y direction. This is going across the harbor, and we know that that equals 100 meters. That is going to be equal to the steady velocity in the y direction, okay? When we're talking about how much displacement in the y direction, we have to think about the velocity in the y direction. Not the overall velocity of the kayaker, but velocity kayaker y. And we just solve for that in the blue. And then you multiply that by delta t. And so this allows us to solve for part B of the problem. This allows us to figure out how much time it takes if the kayaker orients the kayak at 48.19 degrees north of east. How long does it take for them to go across that 100 meters? And so this just simply demands a rewrite where you divide both sides by the velocity of k in the y direction. So delta t will be equal to delta y, and again, that's 100 meters, that's the width of the harbor, divided by the velocity of the kayaker in the y direction. You have all of that now because the velocity of the kayaker in the y direction, which is this right here, is just the velocity of the kayaker, which you know is 3.0 meters per second squared. And then you also can figure out the sine phi because you know that phi is equal to 48.19 degrees. So you would put 100 meters in for delta y, and then you would put the VKY relationship, which is this relationship right here. You would put that right there, and that would allow you to solve for the delta t, which is the amount of time that it takes for the kayaker to keep the kayak going due north, which again doesn't mean that you point the kayak north. You have to actually point the kayak a little bit to the west of north because you have this eastbound current. So if you point the kayak to the west of north, it has an x component that is going west, which could potentially cancel out the current of the water going east. And then you have to figure out, so then what angle do you make so that if you can paddle at 3 meters per second, your x component would be precisely equal and opposite that of the current. When you do that, you then would cancel out the velocity in the x direction, and the velocity would just be due north. So I also want to remind you that when solving this problem, you have to be a little bit careful about how theta is defined with trig functions. And more specifically, theta starts going due east, if you will, in the positive x direction, and then it begins to sweep an angle in a counterclockwise fashion. And so I had to keep that in mind when my calculator reported 131.81, but I was trying to talk about this phi right here. I realized that that was corresponding to theta being swept from the positive x-axis. So keep that in mind. Keep in mind that when you've got vectors in different quadrants, you are going to have different combinations of positive and negative components. And based upon those combinations of positive and negative components, that's going to, from a calculator perspective, report a theta that corresponds to just how far you have swept. Have you gone this far? 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 Where in all of these cases, you have some vector like our kayaker one, and since it starts at the positive x-axis, this theta is defined as the angle that's swept till you get to the vector. I hope you found that helpful. That's going to conclude this review of problem number 10 from problem set 2. This is problem 13 from problem set 2. This is a good problem both for understanding rotational kinematics and how theta is related to displacement, and how the angular velocity omega is related to linear velocity v, and how the angular acceleration alpha is equal to the linear acceleration a. It's also a good problem because you have to do some conversions. And so let's get going here. A bicycle wheel. We've got a bicycle wheel. Let's say that here is the axis of rotation. This bicycle wheel is turning, and we are told that it has an angular acceleration, which we call alpha, equal to 0.47 radians per second squared. We are also told that it has an angular velocity, that's what we call omega, that's equal to 42 RPM, which is revolutions per minute. I'm going to show you right now how we can do a conversion from revolutions per minute to get it to be radians per second, so that we can use it with that alpha term. So if you can imagine, each column is multiplied by each column in this conversion. This is sometimes called the factor label method. Eventually, I have revolutions per minute, and I want radians per second. So I'm going to somehow have to figure out how am I going to get revolutions into radians. So it turns out that for one revolution, you cover 2 pi radians. And that allows me to cancel revolutions. So now I'm in units of radians, so that's good. But now I want to get from minutes to seconds. And so 1 minute is equal to 60 seconds. And see how the minutes cancel out? And so you just multiply the columns. So you would have 42 times 2 pi times 1 divided by 1 times 1 times 60. This would be equal to 84 pi divided by 60. So you could further simplify that. I'm just going to leave it like that for now, because I want to move into the more important thing here, is that now that we have the conversion, we can apply rotational kinematics equations for constant angular acceleration, just like we were able to do so for our linear kinematic equations. And I want to make a case why that is. If you can imagine this bicycle wheel rotating, let's say at a certain time we have this much rotation where you have, and I'm going to blow this up so that it's easier to see. So what I just drew there is essentially some angle theta being swept, such that when angle theta gets swept on the rim of the bicycle, you see the orange I'm filling in here? That is the arc length, which is sometimes defined as S. And quite simply, if there's some radius r from the center of the rotation to the periphery, we say that the arc length that is spanned on that periphery is equal to r multiplied by theta. So in this case, right, this is the r right here. It's the radius of the rotation, and then the theta is the angle that is swept out. I hope you will believe me when I say that even though that orange that I have is curved because it's a circle, I could essentially snip here, take that piece and stretch it out flat like this. Can you see how that arc length could be made flat? It's length. It just happens to be bent, but it's still length. And so this is the key relationship right here, is that if we take into account the radius of rotation and the theta that is swept out, we can then map it back onto a linear S. And once we have a linear S, all of the same equations for constant acceleration that we used for kinematics in one direction or kinematics in two directions, we can also use for rotational kinematics. So let me give you a prime example here, because so part A of this problem, what they want us to do is they want us to figure out what is the angular velocity omega final 5 seconds later. So delta t we know now is going to be equal to 5.0 seconds. Well, with the linear case, we know that if we have a constant acceleration and we're interested in what our final velocity is going to be, then we use the kinematic equation v final is equal to v initial plus the acceleration, which is constant, multiplied by t. We need to know what the initial velocity is, we need to know what the constant acceleration is, we need to know how much time. If I plug in for these values in the linear sense, I plug in the rotational transformation where we simply take r theta, and that arc length is akin to length in regular linear kinematics. I'm going to show you how this equation, the velocity final and the velocity initial and the acceleration, have analogs in the rotational sense, where every time you see acceleration, every time you see a velocity, or it turns out where every time you see a theta, you can have a legend that allows you to map what the linear analog is for the rotational quantity. So since I am taking displacement, which is the arc length, and I am equating that to how far away from the center of the rotation we are, and also what the angle being swept is, that's this equation right here. If I have S is equal to r theta, just like when I took position and took the derivative of that to find the velocity, if I have ds dt that is equal to r d theta dt, which is equal to r omega. Omega is defined as the time rate of change of theta. And I can do another derivative where I can say d omega dt is equal to r d omega dt, and we say that's equal to r alpha. So do you see how for linear displacement we have r theta, ds dt, because s is just a linear distance, that's velocity, and similarly d omega dt is a linear acceleration. And so we have now a legend where we can think of linear displacement as r theta, linear velocity is r omega, linear acceleration is r alpha. Let's go back to my equation here on the left where I want to figure out what the final angular velocity is. I start with the linear equation, and so now I can just say that, well, this rf must correspond to r omega f. This v naught must correspond to r omega naught. By the way, that's what our original angular velocity was that we made the conversion for. And our acceleration, that is going to be r alpha, and that's what our alpha is right here. You see how when I plug the rotational conversions into the linear equation with constant acceleration, I have the r term in every single term, and so it cancels out. And what that essentially means is that we can write down a little legend here where every single one of those linear constant acceleration equations that you've been working with, they are all exactly applicable in the rotational sense, with the one difference is that wherever you see an x for displacement, you put a theta. Wherever you see a v for velocity, you put an omega. Wherever you see an a for acceleration, you have an alpha. So just like I wrote here, you have omega final equals omega initial plus alpha t. That is the constant acceleration in rotational kinematics equation that you'd use, and it's just like the linear one, except wherever I would see a displacement x, which in this case there wasn't one, but if there was, I just put a theta. Wherever I see a v, I put an omega, and wherever I see an a, I put an alpha. So I'm going to continue with this equation because we know what omega naught is. That's that 84 pi over 60 that we calculated earlier. And we know what alpha is. That was given to us. And so we can plug in alpha as well. That is going to be 0.47 radians per second squared multiplied by the time elapsed, which we are also given. That's 5.0 seconds. So that 1 second is going to take care of one of the seconds squared in the denominator, so those two terms multiplied should be in units of radians per second, which is the same as the omega. This was also in radians per second, which should make sense for an angular velocity. So if you plug all those numbers in, (84 pi divided by 60). Bear with me, I'm putting this in my calculator. And then you add the multiplication of 0.47 radians per second multiplied by 5 seconds. As I mentioned on exams, I asked to take answers out to 2 decimal places, so this would be 64.44 radians per second. So that's going to be part A of the problem. To solve part B, we're asked how many revolutions, I'll just abbreviate that rev, in delta t equals 5.0 seconds. We can absolutely continue to use the kinematic equations for constant acceleration that we already know. More specifically, we can figure out how much theta gets swept out in 5 seconds, just like we could figure out how much distance gets covered in 5 seconds. Remember the equation where you would say the total displacement, delta x, is equal to the initial velocity multiplied by the time elapsed plus 1/2 at squared. And remember our little legend, x theta v omega a alpha. Some of you are probably wondering, like, why isn't the r there? Because when you include, remember, this is all based on the idea that if you have some angle theta, your arc length right here, s, is equal to r theta. So the r, if you plug it in, if you plug the relationship into all the equations, the r's are going to cancel, as I already showed you that they cancel out right here. So you can just take the linear kinematic equations for constant acceleration and make these direct substitutions. So I can say delta theta is equal to omega naught t plus 1/2 alpha t squared. And I know what omega naught is. We calculated it right here. I know what alpha is. Alpha is given to us right here. I know what the time is. That's given to us right here. So you literally plug all those numbers in. And in the interest of time, I'm going to leave it to you to plug in the numbers. But one last thing. When you get your total delta theta by plugging all those numbers in, this delta theta is going to be the amount of angle swept. But this is asking for how many revolutions. So it's important to know when you're talking about theta, like let's say like right here, it starts as theta equals 0 in the positive x direction, and then it sweeps counterclockwise. So when it gets to say right here, theta is 90 degrees. When it gets to right here, theta is 180 degrees. When it gets to right here, theta is 270 degrees. When it gets to right here, so it's gone a complete circle, it's 360 degrees. Well, another way of thinking about it is that if we go, say, a semicircle, theta equals 180 degrees equals pi radians. And if we go a full circle, theta equals 360 degrees equals 2 pi radians. So that's what a revolution is. A revolution is a full circle. So once you know, and again, you can just plug all the numbers, all those, like, we know this omega naught because we solved for it right here. And we know the alpha because we're given the alpha originally. And we know the t, that's 5 seconds. So we can then figure out how much theta is swept, and then to figure out how many revolutions there are, what we do, because we've got things in units of radians, theta is going to be in radians. So to determine the number of revolutions, you simply take the total number of radians and you divide by 2 pi. And so that's the number of revolutions that you're going to get. Use this equation to figure out the total theta swept, divide it by 2 pi radians, and that's going to tell you how many revolutions you get in 2, or shall I say 5 seconds. And so that's a wrap for question number 13 on problem set 2.